So our next unit is applications of integrals. And since I like to kind of have a way to bridge from one unit to the next, I wanted to show you kind of an application of differential equations and partial fractions. And that is called logistic growth. If you've taken biology, you've probably talked about logistic growth, and that this is a more accurate model for how populations grow given enough resources. In that, if I look at a graph, if this is time and this is population, then population growth starts out exponential, growing faster and faster and faster based on how large the population is. But then resources are not infinite. So the population growth slows and eventually levels off. And where it levels off, or a horizontal asymptote in math terms, is called the carrying capacity. It is allowed to go above the carrying capacity, but if it does, it comes back down towards it. Because remember, a horizontal asymptote is allowed to be crossed. The function just has to eventually come back towards it. So it's not a hard line that a population can ever go above. It's if it goes above it, the resources are now too scarce, and the population falls until it approaches that carrying capacity again. So there is a differential equation that models this kind of a growth. And that's here, dp dt, the instantaneous rate of change for the population with respect to time, is going to be some constant k, which we call the growth constant, times the population, times m, which is my carrying capacity, minus the population. If I were to graph the rate of change graph is actually a parabola. So if this is, whoops, my apologies. If this is dp dt and this is t, what I get, oops, is a parabola. Because we have, if I get rid of these, I have p squared. Negative p squared means it's going to be opening downwards. Because of that, I'm so sorry about that. I don't know why I keep accidentally hitting the different screens. Because of this, the maximum dp dt, in other words, the maximum rate of change for a logistic growth, is at the time when when the population is at half the carrying capacity. So if my carrying capacity is 500, the population is growing fastest when the population is half of that 500, or 250. If I wanted to solve this differential equation, solving it means it's separable. So I would have, getting my p's on one side, only using multiplication division means I'd have to divide by p and divide by the m minus p. So I'd have the integral of 1 over p m minus p dp equals the integral of k dt. Solving that requires partial fractions. And when I solve it, I get this, where m is still my carrying capacity, k is still the same growth constant that I used in the differential equation. A, though, is not the initial population. It is some constant that depends on the initial population. And when we get to my example, that will make more sense. So things that we can be told. So let's say we have some population where dp dt is given by this differential equation. and we know that there's an initial population of 18, whatever they are. You can decide for yourself. They could be bears, they could be spiders, they can be whatever you feel like. I can see from my differential equation, this is K, this is M. So what is my carrying capacity? Well, the carrying capacity is M, which is 1,000. At what population is the population growing fastest? Well, that's always going to be at half of my carrying capacity, which is 500. So then if I want to actually find the equation that models this, well, that's the P equals M over 1 plus A e to the mkt. Well, I know that M is 1,000. I don't know what A is yet. It's going to depend on my initial population, but it's not going to be equal to it. M times K is 1,000 times 0.0003, which is going to be 0.3 T. To figure out what A is, that's where my initial population comes in. If my initial population is 18, that means that the population when T is 0 is equal to 18. So if I plug 0 in for T, well, 0.3 times 0 is 0, e to the 0 is 1, A times 1 is A. So I've got 18 times 1 plus A is equal to 1,000. By cross multiplying, divide both sides by 18. Subtract 1 from both sides. Which is going to give me 491 ninths. So that means that T is equal to 1,000 over 1 plus 491 ninths e to the 0.3 T. And there is my model.